11. Here today we are going to see equation of continuity. Equation of continuity. What is meant by equation of continuity? We have to derive this. Suppose we consider a simple diagram here. Suppose this is a pipe. Suppose this is a pipe whose area of cross section becomes narrower on this side. See here area of cross section is large and it goes on decreasing. Here area of cross section is small, and through this pipe, suppose you consider steady flow of incompressible liquid. We consider the steady flow of incompressible liquid. Now we consider two sections here. Suppose we consider this is one section. We consider here, suppose this is the another section. Suppose I will give here names. Suppose this is E, F, G, H. We consider the second section, that is P, Q, R, S. Suppose here we consider A1 be the area at this portion, area of cross section of the pipe, and A2 be the area of cross section of the pipe at this section. Now suppose we consider V1 is the velocity. Suppose I consider V1 is the velocity at this portion and V2 be the velocity at this portion. Then in time t, suppose we consider this distance, liquid passes through this distance. I will write here V1 into t, and here in same time this distance we consider V2 into t. Here V1 is velocity at this point. Here V2 be the velocity at this point. Suppose I will consider time as a delta t. Delta t be the small time. V2 into delta t. A1 A2 be the area of cross section. V1 into the velocity at A1 A2. Volume of liquid entering the tube through cross section in time delta t at point A. We have to obtain the volume. See here, volume at A. How will obtain? Suppose A1 is the area of cross section and V1 delta t be the distance. A1 is the area of cross section, V1 delta t is the distance. Then this is the total. I will write here volume, and we consider here, suppose we multiply by rho. This is the mass. Volume of the fluid entering the tube, area of cross section delta t at point A is, we consider A1 V1 delta t into rho. We consider this is the mass. Instead of volume, I will write here mass. That is volume into density is the mass. And for point B, we consider here A2 V2 delta t. This is the volume. We multiply by rho, and this is the mass at B. Now here we consider that is mass is constant. Therefore rho A1 V1 delta t is equal to rho A2 V2 delta t, and therefore we write here A1 V1 is equal to A2 V2, and which is equal to, I will write AV, which is equal to constant, and this equation is equation of continuity. That is, we consider this equation says that the volume rate of flow of an incompressible fluid for a steady flow is same throughout the flow. This is about the equation of continuity. Now we consider next article. that is Bernoulli equation. Bernoulli equation. Suppose you consider same type of pipe. Suppose this is the pipe. We consider this is the pipe. Through this pipe liquid flows. Suppose you consider here area cross section is large and this area cross section goes on decreasing here like that. Suppose here we consider this is the area of cross section, and here we consider suppose suppose we consider here suppose here A1 is area of cross section and here A2 be the area of cross section. Now we consider here suppose two regions. Suppose here this is P, Q and through this region suppose V1 is the velocity. Here we consider suppose this region R, S and here suppose V2 be the velocity. Now suppose this distance is D1. I will write here symbolically D1 and this distance we consider D2. Now here suppose from the ground, suppose this is the ground, and from the ground suppose H1 be the height, and here for point A1 we write suppose H2 be the height. Now here this Bernoulli equation, Swiss scientist Daniel Bernoulli observed in his experiment that speed of a fluid in a narrow region increases. See here, this is the narrow region, but the internal pressure of a fluid in the same narrow region decreases. This phenomena is called, that is Bernoulli principle. Suppose we consider here, I will write here V1, V2 be velocities at P and R. V1, V2 these are velocities. A1, A2 area of cross sections at P and R. Area cross section at P and R. P1, P2 pressures at P and R. D1, D2 distances at P and R. P1, A1, P2, A2. You see, pressure into area. These are the forces at P and R. Now, the volume dV passing through any cross section is, see here, I will write here dV is equal to A1 D1, which is equal to A2 D2. This is the volume, and suppose this is equation number 1. The work done on the element by surrounding fluid flow from P to R, suppose W be the work done, I will write here, that is P1 A1 D1 minus P2 A2 D2, and therefore W is equal to, I will write here P1 dV minus P2 dV. Therefore W is equal to, I will write here, that is P1 minus P2 into dV, and suppose this is equation number 2. Now work again we can write here W, that is work done, is equal to change in kinetic energy plus change in potential energy. Work done is equal to change in energy. I will write this is equation number 3. W is equal to delta Ke plus delta P, and therefore we consider one by one. Net change in Ke in time dt. Here see, therefore delta Ke is equal to, I will write here, half. Kinetic energy is equal to half mv square. I will write here mass, that is rho A2 D2. This is the A2 D2 is the volume multiplied by rho, that is the mass, and V2 square, velocity V2 square, minus half, again mass, rho A1 D1. See here, A1 D1, this is the volume at this point, this region, multiplied by rho, this is the mass, into V1 square. This is the change in kinetic energy, and therefore delta Ke is equal to, I will write, half rho dV. See here, A2 D2 is dV into V2 square minus half rho dV into V1 square. Therefore delta Ke is equal to half rho dV into V2 square minus V1 square, and suppose this is equation number 4. This is the change in kinetic energy, that is half rho dV V2 square minus V1 square. This is the equation number 4. Also net change in P. Now we will calculate net change in P in time same dt. See here, delta PE is equal to mgh. Mg is the potential energy, therefore I will write here mg rho, then dV. dV is the volume, into density means m, into g, into V2, sorry, into H2. H2 is the height. Instead of we write here H2 mgh2. See here, mgh2 minus rho dV into g into H1, and therefore delta PE is equal to, I will write rho g dV and H2 minus H1. Suppose equation number 5. Now putting equations, see here, putting equations 2 means work done P1 minus P2 into dV, equation 4 delta Ke, equation 5 delta P, all these, that is 2, 4 and 5 in equation 3. I will write here putting equations 2, 4 and 5 in equation 3. We get here, what do we get here? Suppose the value of W here, P1 minus P2 into dV. This is the work done. Now change in kinetic energy from equation 4, that is half rho into dV into V2 square minus V1 square plus change in potential energy rho g into dV into H2 minus H1. See here, what happens here? This dV gets cancelled. dV gets cancelled, and therefore I will write here P1 minus P2. P1 minus P2 is equal to I will write here half rho as it is, then v2 square minus v1 square plus rho g into h2 minus h1. Suppose this is equation number 6. This is the Bernoulli equation. It states that work done per unit volume of a fluid. Work done per unit volume of a fluid. See here, P1 minus P2 is the work done per unit volume. We divide by volume throughout of a fluid by the surrounding fluid is equal to sum of changes in kinetics. This is the kinetic energy and potential energy per unit volume. This is the Bernoulli equation. That means we can write here that is therefore that is P1 plus half rho V1 square. See here P1 half rho V1 square, this is minus, here we take to this side, plus rho G H1. See here rho G and this H1 is negative, we take on the left hand side, which is equal to, we can write here P2 plus half rho V2 square plus rho G H2, or in short we can write here P plus half rho V plus rho GH is equal to constant, and this is the Bernoulli equation. Thank you.